Okay, we're going to start recording.
All right.
Get the PowerPoint up here. Here we go. Okay, so we'll do a short review of what we did last time. This is going to be our last talk on foundations, on what is underlying a lot of the stuff that we're dealing with. And so we'll do a quick review of what we did in the first two talks. So the first one that we did here is we're really at this crossroads in science where 5% of the universe, the matter and energy that's there, is what's been studied for the last 500 years by what we call science, and 95% of the mass and energy is dark. We don't know what it is. And we'll offer some what we think are good candidates for what the answer to this is, but right now, there's nothing widely accepted in science. And then what goes with this is this other trend that materialism continues to grow in importance, and people are now dropping out of organized religious groups. They're saying that they're spiritual, but they're not affiliated with any religious group. And now this is the largest category of people in the United States when you deal with this. So we're going to walk through these different issues: mysticism, science, art, and spirituality. These are the foundations of the class. So we had a little background here of the history of science. We had, in particular, gravity, where Newton started saying that there were three dimensions for space, and then there was time, and gravity attracted the pieces of matter to one another. And Einstein showed that space and time were linked together, so that the linking occurred because as you went faster and faster toward the speed of light, time slowed down. So there's a linkage between where you are in space and your velocity in space and time, which wasn't what Newton said at all. And then on top of that, Einstein argued that actually what we call gravity is really due to a curvature in space and time, so that as gravity increases, time slows down, which is not something that Newton said. And we have these funny objects called black holes, aggregations of matter, where the aggregation of matter is so strong, the gravity is so strong that light can't escape from this object. So therefore, since you can't see it, it's black. And it turns out people thought this was just something bizarre, but in fact, every galaxy that we've found so far since 1960 has a massive black hole in the center of the galaxy. The Milky Way galaxy black hole has a mass of 4 trillion masses of the sun. So it's something, really significant. And this is a tip-off that there's more to come here. Ron Cowan observed.
Let's have a little segue. Introduce Ron.
Yeah, Ron is Bruce's brother and
twin brother.
Yep.
Born 40 minutes apart.
20.
20?
Yeah.
Okay.
I'm the older one.
Okay. And Ron passed on in 2019. I worked with him for 3.5 years, and he was able to go through very deep meditation and went back to the start of the universe that we live in today and saw that there was a big bounce there, that the universe was very small, and then it rapidly expanded. But there wasn't any, it expanded, and then apparently it'll then contract, expand and contract. So just like we have birth, life, and death, the universe has the same sort of thing. But
and Hindu scriptures refer to that.
Right. The Hindus
like,
are very clear.
It's like breathing.
Right. And the other thing that apparently Ron observed was there's other universes out there. So there's a space between these universes. I don't know what we would describe it as. It's just a void. And many of these other universes are running around doing their thing. We don't know what's going on. One thing that Ron did discover was in our universe, we have blocks of information that are found everywhere. They coat the compartments of space. Space is a foam, a set of little compartments. So particles hop from one space compartment to another, and you actually get down to that level of granularity and look, that's how things move. They go hop, hop, hop. But the space compartments are coated with the blocks of information that are constantly scanning the universe all around it. And when they detect a change, then there are algorithms in these blocks that say, okay, therefore we have to do the following, whatever it is. So presumably these other universes have the same sort of structure, probably even the same algorithms, but they could have different parameters in them. If you have different parameters, you end up with a different universe. And so it goes. So truly amazing. I don't know what we would call space for the void in between the universes, but it's something. It's not what we would call space. It's not our space, that's for sure. So then we ran through some comments by Einstein here on spirituality and science, and he's very much said that I believe in the God of Spinoza, who's this Dutch philosopher. And Spinoza said, stop praying and pounding your chest, go out into the world and enjoy your life. I want you to sing, have fun, enjoy everything I've made for you, and stop going into those dark, cold temples that you built yourself, saying that this is the house of God. My house, the house of God, is in the mountains, in the woods, in the rivers and lakes and beaches, and wherever I live, there I express my love for you. So this, of course, doesn't square with any organized religion, but it's what Einstein said, I believe in the God of Spinoza. So that takes us up to mysticism in the first lecture. And mysticism today, what we think of it as, is becoming one with God or with the absolute, but it could refer to any kind of ecstasy or altered state of consciousness, or something that's has a religious or even spiritual meaning, but it's something that's different. That's thinking of it linking with God is the way that most people today think about it. And so the Greeks actually were the ones that created the world. The word, let's see, mes, it's micro, mes, and then tuo, meaning too close or to conceal. So when you're mystic, you close things off or you conceal things. And that's where mysticism comes in the Bible and scriptures, in anything involving meditation, and and so forth. So in modern times, mysticism ends up meaning the aim at the union with the absolute or the infinite or God. And this is what most people seem to be comfortable with today when you talk about mysticism. But the people have had mystical experiences of all sorts, and those tend to get dismissed for whatever reason, because they have trouble replicating them. So the one thing that comes through mysticism is the world that we see with our eyes and mind is really an illusion, that it's not a little person sitting here behind our eyes, looking out through our eyes and seeing 3 dimensions of space and then one of time, watching time change as we move around. But in fact, if we go to the Epic of Gilgamesh or the Mahabharata and the Bhagavad Gita, if we go look into the Torah, into the Tao Ching of Lao Tzu, into the Yoga Sutras, into the Abhidhamma and the Four Noble Truths of the Buddha, into what the Essenes and Kabbalistic Essenes saw there, what Jesus the Nazarene and Mary Magdalene.
I want you to look up how you spell Reiki.
Reiki?
Yeah, that's just despicable. You live.
What is it?
Reiki
R-E-I-K?
I'm not gonna tell you.
Okay. I'll look it up. And then the
It's not
Cathars.
like that.
It's not this, okay. And then the Cathars of southern France. And then we have Jung. These are just all examples. There's many, many, many more, but everybody comes back and says, what we see is really not what's out there. That the real universe is different. And what we think is our universe is in fact an illusion. And so what goes with this is that our physical body is linked to an immortal soul, and the soul links to the body at birth and has a set of goals that it intends to achieve in this incarnation. But once it incarnates, it can no longer remember what those goals are. It has free will, but it's veiled from seeing those goals once it incarnates. So you go through life. At the end of life, when you die, you have an assessment of how you did in this life. And in looking at that, you then go look at the goals that you had set. How did you do in terms of trying to fulfill the goals of your life? Now, what Jesus said was our purpose in life is to learn to love yourself, love your neighbor, to show compassion for others. And this means working through the karma of your past lives to grow and to learn. And as you grow, the sense of love grows. So for right now, at the level that we're at, this is the purpose of life. But it shows that our life has a very complicated side to it, an immortal soul, and we go through body after body, incarnation after incarnation. So that was the first class. Now we get to class 2. And we started off by saying there appear to be 2 avenues to understanding the universe, at least 2. So a more classical approach that Western science has adopted is to carry out observations, do analysis, and then interpret what they saw. And this led to the basic theory of electromagnetism. It led to what Newton did for gravitation, what Einstein did. But it does have this problem that it requires observation. And so far, we've only been seeing 5% of the mass and energy in the universe. So we need the other 95% to try and understand the universe, the bulk of it. And that's the approach that we'll take here in this lecture, is that it looks like we need more dimensions to be able to understand what's really going on, which is consistent with what we said before, that what we see around us is not the real universe. It's a quite different universe. Then in the final lecture, which is what we're doing tonight, we're going to come to what's a more modern approach, but actually it's been around forever, where the order or the theory emerges, or whatever the physical phenomenon emerges out of chaos. The classical approach is fine, but it can't account for a lot of orders that we see. And an example is superconductivity. No one had any explanation for it until a so-called theory emerged that was totally different than any other theory that anyone had seen. A different example is a tornado. We have wind, rain, dirt flying around in the air, and all of a sudden order is created when this funnel drops down to the ground. So we're in the world that it emerged out of nothing. Or the final example that we use is we take,
And they're ultimately unpredictable. I thought that was interesting.
well, we haven't been able to predict them yet.
Right, but that's what
Remember, there's no
scientists-
limits to mathematics. There are limits to people. So the thing that happens that is always held up as an example of emergent phenomena is you take a human being and you look, and the human being is made up of 70% water, and the other 30% is a bunch of elements of different sorts. So if I go get 110 pounds of water and all these other elements in the right proportions, and I mix them all up, why don't I get a conscious human being? Because the consciousness emerges out of this, what's going on. And so consciousness is something that's beyond a simple theory that would just look at the piece parts, and it emerges, it's above anything that you could think of for doing this.
Well, but maybe the body emerges out of the consciousness.
And that's what Marjorie said. Body emerges up.
It
so-
might, I'm just saying.
Yeah, it could be. So we start at the beginning, and we took here, this is the gospel according to John. It says there was a void and there was God. And then all of a sudden, God decided to create something. There was light and darkness, and this led to the creation of the universe. So the original universe didn't have any light or darkness. It was just with God, but magically this universe emerged out of all this. And a different example is to go to Genesis, and we see that in the beginning it says God created the heavens and the earth. So there wasn't any heaven, there wasn't any earth, there was nothing. There was and after he was busy creating it, she creating this, there was darkness and there was light, and in the what we call the earth emerged out of this. Okay, so here we go. How are we going to explain any of this? So the path that we took was, we said, well, look at this amazing amount of work that's been done over the last couple hundred years in electromagnetism. And this led to the current view in mainstream physics that there's 4 forces in the universe. There's gravity, where just matter attracts each other, depending upon how massive the body is. The gravitational pull is larger or smaller. It's proportional to the mass. There's electromagnetism, where you have positive and negative charges, and these charges create fields that go out through space, and the positive charges and negative charges attract, and the like charges repel one another. And so this is when the charges start to move, then we start to get waves occurring, and we get things like television and cellular telephones and so forth. Then we had the strong force, which occurs in the atom, where the protons in the nucleus of the atom actually attract one another. In electromagnetism, positives will repel, but in the atom, the protons attract one another, likes attract here. And then finally, there's this weak force, where in the nucleus of the atom, a neutron decays into a proton, an electron, and a neutrino. So the proton stays there, the electron goes flying off into around the cloud of electrons around the nucleus. The neutrino is negligible, and so we end up with what's called an isotope. We've got one extra charge, so the charge is increased by 1, so the atomic number is increased by 1 when this weak force kicks in. So according to current mainstream physics, there's 4 different forces. In fact, there appears to be only one force, which is, we take the current theory of electromagnetism and we include the effects of the ether, the space that's around us all that forms a foam that makes up space. And when we include this, then electromagnetism, strong force and weak force, all are the result of just one field, one electromagnetic field. When it's very, very short distances, then the protons here, which are all positive charge, attract. So it flips. At greater distances, they repel, but at very short distances, they attract, is what comes out of this. And the same thing happens here, with the isotopes that are occurring here. And then what we call gravity is just due to we have this ether, and the density of the ether can change as we have no matter, or we have a little bit of matter, we have some more matter. As the density of the matter changes, then we end up with what we call a gravitational force, and so forth. So there's really only one theory here governing these forces, the etheric electromagnetism, the theory of electromagnetism that encompasses the fluid effects of the ether. And then there's a quantum version of this, which is called string theory, because at the bottom of it, what Ron Cowan observed was there's matter and dark matter. Then the matter consists of subquarks, 3 subquarks to 1 quark, 3 quarks to 1 proton or neutron. The subquarks for matter have 10 closed vibrating strings, and they end up with some energy in there. So it appears to be a particle, but it's more like a jelly resonating inside these strings. Dark matter only has 5 closed strings, and they're actually in 2 different subspaces, 2 different orthogonal subspaces to one another in 2 different 10-dimensional spaces, and so forth. So that was what, again, what Ron showed. We touched on all of this work that was done on electromagnetism over, a century or more, all kinds of work done, which got boiled down by Maxwell into a single set of equations that summarized all of this stuff. And one of the key things here, for example, we've all seen this, is that moving electrons create a magnetic field. So there's electrons in all these iron filings here, and there's electrons in the bar magnet that's underneath this piece of paper here. And when you scatter the iron filings around like this, they follow these lines, as you can see, and this appears to be the north pole of the magnet, and then the force lines go to the south pole. But in fact, even the simple picture, while it's interesting, it's correct because there are iron filings there. Suppose there weren't iron filings. Suppose we could just do this with just the bar magnet. So we did this with a cathode ray tube that was illuminating the phosphors on a TV screen. We just powered on the TV. There's no TV signal to draw on. And we put the magnet there on the TV screen, and we have a little video here that's linked here that shows that the field goes out, just like we see here, then comes around down to the middle of the bar magnet, then comes out of the middle of the bar magnet and goes down to the south pole. But when you have iron filings, those are little magnets by themselves, so they all lined up, north pole to south pole to north pole, and so that distorted this underlying field. So this picture here is correct, but it's misleading. It isn't how the real magnetic field works. And so it goes. Here's what Maxwell did. He put together everything into the small set of equations here. And out of these equations, he discovered that there would be the propagation of electromagnetic waves. And this was huge. And he thought that the waves would be light waves. So this is how light would actually propagate through space. Now, what Maxwell missed was, if you see the wave coming at you, then like a horn on a train, then as a train comes at you and it's going fast, then the waves get crunched. The wave fronts are compressed toward you. They're what is called shifted toward the blue part of the spectrum. And then when the train gets by you and is going away from you, then the waves are stretched out, so they're shifted toward the red part of the spectrum. And with the exception of light, which is what Maxwell was dealing with. And in this case, the speed of light is the same no matter whether we're on the train or we're standing there watching the train coming. The speed of light is the speed of light is the speed of light. And so Maxwell actually anticipated by, if he would have thought about this, he would have realized that Einstein's theory of special relativity that came out in 1905, he'd actually done it in 1860. And then we had Tesla. So Tesla, not Marconi, invented the first AM radio. And Tesla, not Edison, devised the power distribution system that we use throughout the world. So we have motors and we have generators, and the generators convert typically mechanical motion from, say, water or wind into electricity. That's what a generator does. And then the motor, we have outlets all over the place that we plug into, and electricity comes out into the motor and converts into mechanical energy, typically vacuums and dishwashers and so forth. So Tesla did all this, and he ended up playing around with this, though, at currents and voltages that varied hundreds or thousands of times per second, which is different than what people before him had done. They were incapable of generating things that could run at those speeds. And when he did this, then he observed waves that weren't simply the waves that Maxwell saw, but he also ended up with other sorts of waves called longitudinal waves that you get, for example, when I tie a rope to a pole and snap the rope, a wave goes down the rope and gets to the pole and then bounces back toward me. That's a longitudinal wave, different than what we think of as electromagnetic wave, but it's still electromagnetic. And so Tesla started using this and tried to figure out how we could use this to have free power, have electric power distributed everywhere, or end up being able to create vehicles that would fly through the air. And he also built an electric car, which is here, and it had no motor to it. It had no source of anything powering it. It just ran around, and everyone, of course, made fun of him, like, what's going on here? But that's who Tesla was. And then we touched on this other chap. Maxwell was credited with developing these equations for electromagnetism, looking at all these experiments. And what was missed, in my opinion, is there was a German, Hermann Grassmann, shown here. And in 1847, he published a book where he derived all of Maxwell's equations and more. And basically what he did was he generalized the notion of a gradient of a function. So I took a scalar function, maybe of two variables, three variables, x, y, z, and t, four variables. And he ended up computing its gradient, which he called the exterior derivative. And that gave him a vector. And then he took the gradient of the vector, and that gave him a field. And then he took the gradient of the field, and it gave him a current, and so forth. So this was all done by Grassmann in 1847. The basic problem was no one could understand what Grassmann was talking about. It just seemed to be magic to everyone, and it was far beyond what anyone could do. And in fact, it was only realized, in the 1920s, 1930s, that Grassmann had done all this stuff, 100 years after he'd done it. There is one little funny thing here that comes up in all these things, which is if we take the speed of light squared, we multiply it by the susceptibility of electric fields and the permeability of magnetic fields. These are parameters that arise coupling pieces of electric and magnetic fields to one another. Then we end up with this relationship that this is intrinsic to Maxwell's equations. And no one knows where this came from. But I asked Ron Cowan's former incarnation, Emmy Noether, who was always in our conversations, what in the world was going on here. And she said, oh, this is simply due to an identity you could derive from some combinatorics of the nature of how space and time work with one another. Of course, it's so simple, I'm not going to tell you how to do it. So that was the end of that. We'll just file that away as something. Here's a little description of what a gradient is, where you see things having, if it's flat, the gradient is relatively small. If it's steep like this, then the gradient's very big. And we compute the gradient of the gradient. Say we go around a corner like this, then that's a very rapid change in the gradient of the gradient, very big. Whereas here, the gradient is pretty constant, so it goes small and so forth. So Grossman did all the stuff. He dealt intrinsically with complex numbers, and just a little review we put in here. Complex numbers, we have a real part and an imaginary part, and the complex number here is the real part plus the square root of -1, which is I, times the imaginary part. So there's two real things, A and B, but B is multiplied by the square root of -1. And the thing to take away from this, we need this in algebra. So we have the equation x squared equals 4. There's two solutions, +2 and -2. I plug either one in, I get x squared equals 4. If I have x squared equals -4, this has two solutions also, +2 times the square root of -1 and -2 times the square root of -1. So if I plug this in, these are also solutions to this. So it's not a luxury that we need this. We have to have this. And one of the consequences of this is if we had a purely real number, when we multiplied it by the square root of -1, we'd swing it around so it's totally vertical here. Or in other words, we would now rotate it by 90 degrees. And that's what Ron Cowan did in doing this stuff, as we'll see in a second. So I mentioned before, there's two of these things here, the magnetization M, the magnetic field, and the magnetic induction. And these are all come out of Maxwell's equations, and they're hidden in there. But here we see this susceptibility factor here, and in electricity, here's the electric field, here's the permittivity of the electric field, and here's the displacement field that we get, which is really the thing that does the work. So that's where these things show up. So the reason for going all through this is that back in 1970, I was in grad school, and my doctoral dissertation advisor at Harvard, Roger Brockett, asked me to investigate Grossman's work, which I did, and I came back with all of this stuff for what Grossman had done. I couldn't find it anywhere in the literature, but I ended up publishing this when I was at Bell Labs, and I did what's called a commutative diagram connecting all of these different things. You go from a scalar to a vector to a bivector to a trivector to a quad vector, and so that you end up with what in algebra is called a commutative diagram. And so that was something original that never appeared there. So I published that, but I realized that there was nothing here that had to do with physics, because all it had to do with was taking gradients of gradients of gradients. There was no physics involved here. And so where did the physics go? What's going on? So the physics came in when I found in 2005, which was obviously 35 years later, this classic text by Arnold Sommerfeld. And on one page, he showed the equation of electromagnetism, and on the other page, the equations for the mechanics of a perfect or frictionless incompressible fluid. And the two sets of equations are identical in form, with the difference that the fluid mechanics equations include extra terms for the density of the fluid, not surprisingly. So it doesn't take too much to plug in what's going on in electromagnetism and include for the density of the ether, the medium that allows electromagnetism to propagate and so forth. And then you carry out a what's called a perturbation analysis, where you expand in the zeroth order of these things. So the zeroth order, anything to the zeroth power is 1. So the zeroth order terms really are just Maxwell's equations. But if we include terms of the first order, first power and the second power in the density of the ether, then we came back with terms which are the strong force and the weak force here coming out of this. And gravity was, in fact, the result of the change in the density of the ether, which is actually what Einstein had shown. And all of this had to be known to Tesla. So we then had this crisis of dark matter that was discovered in the 1930s, when they put in some estimates to see what are these galaxies that they could finally see with the telescope stable, and they concluded if they just looked at what they could see, they were unstable. But if there was extra dark matter here, in fact 5 times as much as the matters we could see, then it was stable. So that fixed that. The only problem is, where is it? No one could see it. And the other piece was dark energy, which is where all of the galaxies that we could see were going away from one another. And in fact, this energy was called dark energy because it was space itself that was expanding. And this is 68% of the mass and energy in the universe, a huge contribution. But how do we measure this? How do we even find it? So what Ron did was he observed here this, that we're actually in a 26 real dimensional space. And we had 4 dimensions here for space and time, for matter. And then there were 6 compactified dimensions here. And that gives us a 10-dimensional space for matter. And all the dark matter is, all of these are multiplied by square root of -1 from the one to the left, so that they're all rotated by 90 degrees away. So the dark matter 4 dimensions are right next to us, but we can't see it in the 4 dimensions that we're in. And similarly, there's another 6 dimensions here that are orthogonal to the 6 dimensions here. And in these 10 dimensions is where dark matter lives. And then there's some synchronizing 6 dimensions here that connect between these 2 different 10-dimensional subspaces to make sure that everything's working okay. So the basic idea here was that if we had in 3 spatial dimensions, we had 5% of the matter in the universe, then if we took 3 and divided by 0.05, we need 60 dimensions to account for everything, more than just 3, which matches, again, what we suspected. And what Ron observed was there's actually 24 real spatial dimensions, or if we did these with complex numbers, this would be the real part over here, for example, in this 10-dimensional space. And this would be the imaginary part here. And we would end up with half as many, just 12 complex spatial dimensions. So what happened then was, this is just a repeat of what I just said, so I'm going to skip over it. What is this compactified dimension? It's actually wrapped around, here's two compactified dimensions wrapped around one particular direction. Oops. So you can see here that if it's wrapped around it, but the scale is very, very small. It's 23 times the size of a piece of space. The space is measured in what are called Planck lengths. So what we ended up with here, in 1926, the German mathematical physicist Oscar Klein came back and said, well, you need these extra dimensions are compactified. That's why they're there, but you can't see them because they're so small. and that appears to be the case. They're built on these what are called Calabi-Yau manifolds. Here's pictures of two of them. There's apparently roughly 10,000 of these Calabi-Yau manifolds out there, and they have all kinds of interesting properties. You can find movies on them on the web. These things all morph and change. You can see that there's holes floating around in these things, and so it goes. And Calabi and Yau, Calabi proposed these things. Yau showed they existed. If you're a mathematician, just because you say something is there doesn't mean anything. You have to prove they exist. And Yau was the one that did it. And for this proof, he got the Fields Medal, which is the equivalent of the Nobel Prize, but in mathematics. So the main thing about these Calabi-Yau manifolds is that they're very flat. If you take a look at all these pictures, see a lot of flatness everywhere, but they have these holes and these curvatures occurring in them, and that leads to some interesting things. The one thing we touched on was the holes in these things, and when we looked at this for matter, the compactified dimensions had 3 holes, the compactified 6 dimensions had 4 holes, and the synchronizing space had 8 holes. So the 3 holes link up with the 8 holes from matter to the synchronizing manifold. The dark matter has 4 holes. That takes care of 4 holes in the synchronizing manifold. And the final hole in the synchronizing manifold connects one of the 2 6-dimensional dimensions that's there. So there's really only 10 dimensions, 18 total, but we have 8 holes. So we end up with 10 real dimensions, which matches what the Kabbalists saw in the tree of life, and the end result of this is that this might indeed be true. A different reason why to believe this is we have an electron here. And this is a picture of the standard model showing the electron with 2 resonant states here. These are all quarks out here running around, and this is an electron neutrino that has 2 resonant states. If we have 3 holes, then what mathematical physics has shown is that the electron will have 2 other resonances. So here they are. So there's really only 1 electron that resonates in these other states. There's really only 1 electron neutrino that resonates in these other states. We still have all these different quarks here, but those are made up of subquarks, which haven't been discovered yet. And then here we have these bosons running around here, which is what we said, the strong force, the weak force, the force due to photons and so forth. All of these are really one sort of photon, one sort of boson here. And in the middle is this Higgs boson, which I asked Ron to go observe, and he did indeed observe a matter Higgs boson and a dark matter Higgs boson, both at the bounce when our universe was created. So the Higgs boson really does exist, but there's 2 of them, one for matter, one for dark matter. The only thing about dark matter would be there's no notion of charge here. So there's just 1 subquark for dark matter, and because of the 4 holes, it'll have 3 other resonant states, and that would complete this picture. Plus, we have to include the space compartments. So that's it.
Talk about, I want to aim you at the Higgs boson.
What is this? You want to aim me at
The Higgs boson, and what that is.
the Higgs boson? Is when the universe first did its bounce, there was no mass anywhere. Everything got crunched, and the Higgs boson had a value of 0. So after this expansion occurred, it's called inflation, and then the Higgs boson appeared, and it took on a number. But the number that it took on, it's a scalar. It's a number that multiplies the mass of everything we see in the universe. So all of the matter particles here all took on mass all of a sudden in different ratios that are governed by the intrinsic algorithms that make up our space-time. And that Higgs boson did that for matter, and the Higgs boson for dark matter did the same thing, gave a value of mass. Up to that point, there was no mass. Everything was it was looking at Maxwell's equations with no ether. It was just what Grossman had discovered. So now we get into time, and we said here in the space dimension, sorry, we have 4 dimensions for space time here for matter, and 4 for space time here. But in fact, if we're going to treat time differently here. So the time for matter is going to be, there's really only 24 spatial dimensions and 2 time dimensions. And what we're going to be talking about here is for what we call matter, the time will take on one set of attributes, and for dark matter, it'll take on other attributes. And so for matter, what happens is that the time creates timelines. At every instant that there's a transition of any sort, we end up with a different timeline, a different world. And there's splitting upon splitting upon splitting. And so what basically happens is we end up with a cloud of possible timelines that we could be dealing with. And that goes on and on and on from the start to the end. And this particular theory ends up being able to deal with, it gets rid of any sort of inconsistencies in quantum mechanics by giving you this degree of freedom. But you end up with an uncountable number of universes, but you end up with these things clustering here in such a way that there's certain classes of timelines that are more preferred than others. And so we're in a particular timeline, and there's other timelines nearby. For example, another timeline where the South actually won the Civil War has been discovered when people did this past life hypnotic regression. There are a large number of people that they came across that said, oh, the South won, when in fact the timeline that we're on, the North won the Civil War. So this is just one example of the world we live in. A different example was what Nostradamus talked about. He suggested, here's what the future could look like, but it doesn't necessarily have to look like this. And he described a future that would create Napoleon and then Hitler. And then the third individual was going to be the Antichrist, who would create the Third World War. But we're past that point in time now that Nostradamus talked about. So our timeline has missed that particular thing.
Maybe it just hasn't happened yet.
No, yeah, Nostradamus
Go
is very.
back for a second. Talk about that's Schrodinger's cat in the box.
Well, Schrodinger's cat in the box is shown here, and the cat is in the box. The box is sealed, and there's a
Gas.
There's a vial in there which contains a substance that if you take the stopper off the bottle, or if you break the bottle, the substance will turn into a gas that will kill the cat. So that's what you have. There's a cat in the box and the vial. Okay. Now the question is, maybe the vial broke and the cat is dead. Maybe the vial didn't break and the cat is alive. So which one is it? Is the cat alive, or is the cat dead inside the box? That is the question. And quantum mechanics says, well, you could have both of these things. But in fact, based on this many worlds interpretation, there's 2 different timelines. In one timeline, the cat is alive, and then the other timeline, which splits off here, the cat is dead. Sorry, this is the one where the cat is dead here, and here you can see the cat is alive. So that is an example where it resolves this paradox. How could the cat be dead and alive at the same time? Because you're in different timelines. Now, the thing that happens here is apparently this dark matter, with the time that it has, it actually is having an Akashic record. So the Akashic record captures all of the events for a particular soul on all possible timelines from the beginning of the universe to the end. And so this is what anything in your life, when you have a review of your life after you've died, you end up in consulting this Akashic record to see what happened, and so forth. So the Akashic record is how since it starts at the beginning of the universe and goes to the end, I can hop around on this Akashic record timeline, and I can go see, what is my future like? When am I going to die? Or what am I going to incarnate in my next life? Or what was I 2,000 years ago? What was I doing? And so people have used this in hypnotic regression to reach the soul of someone and try and see what they saw here. Now, the problem with this is that it's discovered here that you end up with animals having incarnated. That is, people have gone in to be animals. In fact, some people have decided to incarnate into trees or into insects or even into stones. And they incarnate into a stone, and it's nice and quiet, and they just sit there for a while, and then they decide, okay, it's time to end this, and that's the end of that incarnation. So the problem that you face here is you end up with many of these things that happen here along the way. The Hindus were the ones that popularized this as the Akashic records, which encompass everything, and they viewed it as a thread, one for each soul, and the souls can incarnate in different ways along the way. So this notion of time, the two different times we have, one for matter and one for dark matter, where our soul is, are very different. And so there's a gazillion unanswered questions here about all of this. We have no idea really how to answer this, but we'll come back to it. But again, this is all due to Ron Cowan. He published these two different books here, The Path of Love, The Future of Buddhism and Science, and How Mindful Meditation Works, Modern Buddhist View. These are available on Amazon. You can go get them and look at it. The book on Buddhism as a science, Ron observed the 7 chakras that you have, and he observed that they were actually dark matter. So that you have these 7 chakras, but your soul apparently links up to these dark matter chakras and runs up and down. They're all interconnected and communicating with one another. And it was just too much of an effort to try and spend any time observing this. There were so many other things to observe, we gave up and just left it for other people to go deal with. And the chakras are well known to anyone that studies any of the mystic texts. There was a lot of curvature that Ron observed. We still don't know what to do with the curvature in terms of relating it back to physical properties. The issue of duality of matter being a particle and a wave occurred in this double slit experiment, and Ron resolved this because he saw that in fact an electron could go through a single slit and it would just be a line of electrons on the far side, or if it was 2 slits close together, then it would form an interference pattern like a wave, and the electron would become a wave as soon as it detected there were 2 slits there, which the electrons constantly scanning, and then and the scans that are occurring due to these blocks of information that cover the electron, they cover the proton, the neutron, and all the compartments of space. So all of these things are sensing any changes. Once they sense there's 2 slits, the electron becomes a wave. When there's 1 slit, it becomes a particle. And that's why this picture is shown here with information and encompassing everything, linking everything together in physics, chemistry, and biology as being the underlying controlling mechanism for everything that we see here. And so it goes. So huge accomplishment. And then there are other people, Louis de Broglie and David Bohm ended up developing this theory of the duality of matter and energy. And Ron confirmed it through these observations here, where here's the first picture you'll ever find of what an electron looks like, 10 strings with some energy grouped into it. So it actually has a hole down the middle. It's a torus, but it's all covered with blocks of information.
These are Ron's illustrations.
Yeah, Ron drafted these. So that gets us up to today. Here we are. And we're going to start off with, we talked about these emergent theories. So a lot of this was driven by Phil Anderson, who for many years was at Bell Laboratories. He received the Nobel Prize in Physics in 1977. And just so you would know, the way that Nobel Prizes work in physics, if you discover a new particle, you get the Nobel Prize next year. If you have a new theory, you don't need to worry about that for 10 or 20 or 30 years, because no one believes. Theories are cheap, and there's lots of theories out there, but Anderson had so many theories that were, tested by experiments in things related to what is called anti-ferromagnetism, or he ended up with a discussion on particle physics where they had so-called breaking of symmetry. The breaking of symmetry is what we touched on when we talked about Maxwell's equations. They were all symmetric, but then we added this ether to it, and the symmetry that was there got destroyed. So Anderson actually had a huge impact on high energy physics, but he was doing this from the point of view of solid state physics, or what he came to call it condensed matter physics. So,
and what years were you at Bell Labs?
I was there from 72 to 84, and he was there from, I want to say, like 61 to 84. He retired to Princeton at that point. But all of the work that you see here, all of this work, he came up with the original ideas for string theory. He came up with the ideas of the Higgs boson that Higgs picked up on and ran with. He had lots of ideas on superconductivity and so forth. But the key thing we're going to deal with here is he was the one who said that there's emergent phenomena that emerges out of chaos, and it has order. And that's what we do in physics, is find the relationships for this emergent phenomena that has order to it. So one time I would go to lunch regularly with the physicists, and Anderson was there one time at lunch, and he was asking these very basic questions about this one area of physics. And afterwards, these guys are saying, they knew how smart Anderson was, and they couldn't believe he was asking these very basic questions. Well, it turns out that the reason I was asking those basic questions was he rewrote the foundations of that particular area of solid state physics. And he received an award 3 years later for explaining all these things that no one had understood. But the way that he attacked these things was he went back to basics. That's why a lot of times very senior faculty will like to teach introductory classes to freshmen. It's because the freshmen will be asking questions that they've never heard before, because the freshmen don't know what's going on. And when you're in the middle of doing something, you get so caught up in the weeds, you forget that you missed this and you missed that. And so Anderson was great at going back to just stepping back and coming up with basics. And his contributions, he legitimately deserved the Nobel Prize in physics. There are other people who got the Nobel Prize in physics who, in my opinion, were just lucky. So what we're going to do here now in this section is talk about these emergent theories that show up in the universe. But actually, if you thought about it, we already covered one. The first emergent theory was what we covered in the Gospel of John and Genesis. There was a void, and then there was space-time with 24 spatial dimensions and 2 time dimensions. And so you look at this and you say, my God, this is absolutely mind-boggling artistry here. this order that's been created. How would anyone come up with 24 spatial dimensions, 2 time dimensions, and having all of these holes in these things of the curvature of the space? And you know, it's not an accident. This is a work of art, but this is only one possible universe that we're in. This is the one that we keyed on, that we think is what's going on. But there's going to be, as you'll see, other theories here. So here we started with a classical theory where we took electromagnetism and added an ether to it, and that was all fine. But if we wanted to actually deal with the conduction of electrons in a material, there's 10 to the 23rd electrons in a cubic centimeter of any sort of material. So we have to have 10 to the 23rd equations keeping track of all these electrons. And there's no way that we can see the intrinsic order that's there. And so what happens as an example of this is, as you take any material and you lower its temperature more and more, it gets sufficiently cold, the material goes from being a conductor to being a superconductor. All of a sudden, the resistance in the material drops to effectively 0. And there's no magnetic field that can enter the material. So all of a sudden, there's this order just due to the temperature. And on the other hand, you know, people, this is why the physicists think they've done everything, is because they have these equations for quantum mechanics or for general relativity, and they say, well, out of this comes chemistry. That's all true. Chemistry does come out of it, but the theories of chemistry are these emergence theories. And then the theories of biology that come out of it are based on the chemistry. Yeah, that's true, but they're emergent theories. They're different theories for biology that would come out, and one of those theories would be consciousness in biology. So you have this very complex entity, and all of a sudden, out of it comes an emergent theory, an emergent behavior that you just wouldn't see any other way. And this was what Phil Anderson popularized here as an approach to physics. Nothing can really be calculated exactly from these microscopic equations, but these more macroscopic systems end up being the ones that give us all the insights into what's really going on. So the first example we have is a tornado. So the tornado is here coming down to the ground. There's all kinds of clouds up here, rain, wind flying all over the place, dirt. And somehow out of this incredible mess of chaos, all of a sudden a tornado will form, which you can see has incredible order to it. It's running around like this, and it goes all the way down to the ground. And yet there isn't any parameters that you can come up with based on how much air there is up here, what the air density is, the water density, how much dirt is flying around. All of those things won't get you anywhere to explaining how this tornado formed. So you need a different theory to explain this emergent phenomena here. Another example is what's called the soliton. In fact, you can actually have waves. The waves were first observed in 1834 by someone in England. Sorry, he was in Scotland, and he was walking down a canal, and the barges were being towed down the canal by horses, and they generated a wave. And he started to follow the wave, and the wave went on for miles. Normally what happens with waves is there's some element of dissipation in them. So the wave at some point will die out. It will no longer be a wave. But in fact, these waves went for miles, and they actually were analyzed, but not until the 1960s by a group of people at Bell Labs. And they gave it the name of a soliton because it's a solitary wave. It comes out of nothing. Why does this one type of wave go on forever and the other types of wave die out? That was what the question was. And so this takes us back to the real mystery of the world, is how we can even understand it, how we can have these simple equations like Newton came up with, like Einstein came up with, like Maxwell came up with, and so forth. But when you talk about this effectiveness of science, that by itself, there's a few examples we can talk about here that do this, but there's many more that we can't explain. So don't think that we've covered everything here in doing this. The success in science is very thin. There's not a lot of things, and especially when we start to deal with all these other phenomena that we talked about, we have a long way to go. We know virtually nothing about what's going on. So the examples we cited were Newton and celestial mechanics, and he just said, oh, gravity is a force that two bodies attract one another proportional to their product of their masses and inversely proportional to the square of the distance. He never said what gravity is. He never described it. He just gave this rule here for describing what happens with the gravity, but that was good enough to answer a lot of questions. Similarly with Maxwell and electromagnetism, that he ended up having a set of equations, and he ended up being able to predict out of those equations that there'd be a wave propagation. But it took another 20 years for Hertz to be able to generate an electromagnetic wave that could be actually measured, and then things evolved from there. And so that is an example. Einstein modified Newton's theory of gravity, but the modification was it was a very simple idea. He was just thinking about someone in an elevator, and he realized that if you're falling in an elevator, this is exactly what would happen to you when gravity is tugging on you, okay? The elevator's falling, you happen to be falling with the elevator, so the elevator is attracted down by gravity, but you're in it. And so just this simple idea explains how Einstein came up with general relativity. Sure, there's lots of equations and all kinds of other stuff, but you end up being able to make predictions 100 years later that you couldn't have made unless you had this framework to work with. And similarly with quantum mechanics, dealing with the atom and what happens there, you end up with the capability now to make predictions to something like 10 decimal places. 10 decimal places. Ask yourself how many things you've ever measured to 10 significant figures. It's mind-boggling. And all these experiments have confirmed that, and they pushed it to sometimes to 11 significant figures or even 12. But so people say, well, why do you think that this is all simple? It's all simple because at the core of it, there's some simple idea that all of it is based on, and that leads to everything. But if you don't have that idea, you don't get anywhere. That's what the problem is in science. So the current thing that we have here, the standard model we talked about, and the string theory model that tries to explain what's going on here. The basic problem with string theory is, to date, after string theory has been around, as we said, since the 1960s. They have yet to come up with an experiment that could actually confirm any predictions. They have trouble writing down any equations whatsoever for string theory. And you say, well, how in the world is that possible? Yet what Ron observed was that the strings are essential or critical to these subquarks, which are in everything, and that they're actually on the right path, but that they can't see what Ron saw. They don't have any instrumentation for doing this. And that is the crux of it right there. If they had that, then they would be able to do all kinds of things, but it is what it is. The other thing that happens here is there's always this very simple physical insight. So this great physicist, Paul Dirac, said, well, I derived this equation in quantum mechanics that allows to incorporate things moving near the speed of light. So electrons probably move at the speed of light inside atoms, not at the speed of light, but very close to it. And so his equations describe that. So he said, well, my equations now describe what happens in physics and in chemistry, where chemistry has to do with, for example, how the electrons behave. Well, that's all true. The only problem is you can't calculate anything whatsoever, because we said you need to get 10 to the 23rd electrons to be able to describe anything, and there's no way you can take this theory and do anything like that. So the same problem occurs up in biology to compound it, and so it goes. And so there are going to be emergent theories in solid state physics, which you would, or condensed matter physics, which you might call chemistry, because that is a way that to describe behaviors of materials. But the same thing will occur in biology. There'll be emergent theories there in biology to explain what's going on. We just don't know what they are. And other examples are, there's a phase transition. I take a lump of ice and I melt it. Eventually it turns into a liquid. If I keep heating it up, the liquid turns into a gas. And here we have all of these different things. So how do I determine what points do I end up transitioning from a solid to a liquid and from a liquid to a gas? What model would explain this here? Very basic question, and yet we don't get this out of Maxwell's equations, for example. Another example is to take a magnet. If you heat a magnet up more and more, at some point it stops being a magnet, okay? So at what point will the magnet being heated up not become a magnet? Well, that requires, again, a different sort of theory here that results in explaining that, but it's not the theory that you or I would be comfortable with from dealing with a single electron, for example. And other examples here basically boil down to, we look at models that are built on models that are built on models that are built on models, and this ends up being what underlies a lot of these emergent theories. So the emergent theories have behaviors that don't involve any of the parameters that we started off with at the bottom, but they work. They're great theories. Then we have getting away from the complications of these models that are again incredibly complicated, and so we just try and simplify these things. But in simplifying them, we throw out everything to get there, and that is the nature of what emergence is. Superconductivity. Here, we said we drop the temperature of anything, and it's low enough temperature. This was discovered in 1911. The temperature drops enough, then the conductor becomes a superconductor. There's no resistance in it, which means that you can transmit over long distances if you can keep everything at that same low temperature, and there won't be any loss. It's a lot of the cost that arrives in transmission of electricity is due to losses in the transmission lines that mean we can only go so far, and then we have to do things. So the net of this is that there's a theory that explains this, but the theory is bizarre. The theory that they came up with to explain this, I'm just looking here to see, is the, here it is, it's on the next page. Three people, Bardeen, Cooper, and Schrieffer, in 1957 came up with a theory that said that what happens as you cool it enough is the electrons that are there pair up. So this sounds familiar to what we saw in particle physics, where the protons in the nucleus that are all positive charge attract one another. The electrons pair up. They couple to one another, even though they're opposite charges, because they are actually vibrating. They're generating, the vibrations generate energy, and that energy is greater than the repulsion that they have here. And so that's because they've cooled things enough. So the net of it is that these cooled electrons, by pairing up this way, are transmitted with no loss. They become superconductors, and the people that did this got the Nobel Prize, and so it goes. A different example, in 1986, there were some materials called cuprate perovskites that are ceramic materials that were superconducting above 90 degrees Kelvin. Now, the stuff that we were talking about before was all done at 3, 2, 1 degree Kelvin, and 0 degree Kelvin is the lowest you can go. There's nothing below it. So the end result of this was no one could figure out how something could work at a quote unquote much higher temperature. It's still 183 degrees centigrade below zero, but it's a lot better than minus 270 degrees centigrade. And so they went through all this stuff, and surprise, surprise, Phil Anderson ended up coming up with a theory that in fact explained what was going on here. So superconductivity is held up as the poster child for all of these things, but there's many other theories that are now showing up that are emergent, and we just listed some of them here. There is a non-superconducting metal film is placed onto a magnet. You can end up having it be superconducting due to this theory that was developed, or there's an actual new theory of superconductivity that results in the flow of single as well as paired electrons that makes this thing work. And it'll just go on and on. There'll be more and more these theories. So the one that the biologists all hold up is consciousness. And so why is consciousness emergent? Well, it just appears. How could this be? But now there's a lot of evidence that animals of all sorts have some measure of consciousness, whatever that means. And what goes with it is that there's some inner life, there's some notion of private thought or imagination or volition, and so it goes. And in April of this year, there was a New York Declaration on Animal Consciousness, where the researchers said there was a 1974 essay, "What is it like to be a bat?" And they determined the bat was probably conscious to a certain level. And so this built on that to say that animals themselves are conscious, and therefore one might speculate that they have souls, that it's reptiles, amphibians, fishes, mollusks, you name it, all have some notion of consciousness. Gravity, going back to physics, it could be an emergent phenomenon with what happens in space and with the matter there. This suggests that gravity isn't really the fundamental force, but emerges from the collective behavior of these more basic components, like the quantum information that we were talking about before. And so a lot of people are exploring this. This takes us over finally to mathematics, which you've been walking around. And it appears mathematics has this hidden order. There is an emerging structure called Langland's program, which is connecting different areas of mathematics, in particular number theory and geometry, to group theory, the study of symmetry, and to harmonic analysis here. And this is occupying hundreds of mathematicians right now, as they're realizing that this has been staring them in the face. And so there's all kinds of connections or symmetries between things that no one thought there was any connection with, which is resulting in the so-called emergent order in mathematics. And the ways that they go about this and what's happened, it's a very rapidly evolving area. So I'm just going to skip over this, but it's something that I think we'll see a lot more of in the near future. In the next 10 years, there'll be a lot of amazing announcements here. We saw one of them in the classification of symmetry of these finite simple groups after they started in 1832 and went at it till literally 2004. And there were many, many papers published, and they came up with 20 different categories of symmetry here. Here they all are shown in a table, but there are 26, 13 here and 13 here, 26 categories of symmetry that don't fall into the major categories up here. Well, isn't it interesting that Ron observed 26 dimensions? And so is there some tie between these 26 so-called exceptional or sporadic groups that are here they're intrinsic to the study of symmetry results in 26 things that aren't really symmetric. They don't fall into the general category. And maybe this has something to do with the physics that we see around us in the 26 dimensional space that we have. This takes us to art. We're just going through everything here. So the term art, there is all these things, there's no generally agreed definition of art, and it's interpreted in all kinds of different ways. But there's visual art like painting and sculpture and architecture. There's theater, dance, and performing arts. And then there's literature, music, film, interactive media. And so all of these things together make up art. And this results in something that we view as beauty. There are conceptual ideas here. It's a human activity that appeals to many people. Now, until the 17th century, art referred to any skill or mastery. So there was no difference between crafts and sciences and art. But the modern usage since then is that the aesthetic considerations are really critical. And so the fine arts are separated from the decorative or applied arts here, thing to keep in mind. And there's a huge amount of creativity, just like in all the other things we've covered here. And we end up with something called aesthetics. Do we really like this? And we end up with realizing now due to brain scans that they've discovered there's one particular area of the brain that is open to pleasure. So this is the pleasure you get from having some really great food, great sex, addictive drugs, an incredible experience in art or music, some great rock concert, love for some friends and loved one. It's an incredible pleasure area that is the same sort of pattern across all these different activities that take place there. And so it goes. Spirituality. Well, spirituality, the meaning of this has changed over time. Traditionally, it was tied into the religious process. So these are the aims to recover the original shape of man in the image of God. So the founders and the sacred texts of the religions of the world, dealt with this. But in early Christianity and in other areas, this really is starting to refer to our life oriented toward the Holy Spirit, or including mental aspects of life. And in modern times, the term has spread to include other religious traditions and all kinds of things related to meditation and esoteric or religious traditions here. So spirituality, again, is one of these things that isn't well defined, but it's critical to all of these things. So the modern uses of this end up with talking about going into a sacred space where the deepest values and meanings occur. And typically this occurs under deep meditation. So the concepts we dealt on before, we have the soul that's attached to the human body. It apparently is linked to these 7 chakras, which are shown over here. And the mind is somehow a little piece that's attached to all this, just like the soul is attached here off to some essence that is a collective unconsciousness, as Jung calls it, that is everywhere, that coordinates everything. And finally, we come to this question of, since we're dealing with ourselves, is anybody else doing this? Well, in all likelihood, we aren't alone. So there's probably other places in this universe where all of this has been dealt with, probably much more than we've ever done. And the last century, what we've seen through all of these telescopes is where there's now at least 100 billion galaxies in our universe. And since the early 1990s, there's thousands of exoplanets that have been observed around these other stars, which suggests that the majority of all stars have planets of some type. They're not necessarily habitable planets, but they have planets. But there's so many of these planets that at the end of the day, the odds are that there'll be lots of planets that will have life on them. And if that's the case, then some of this life could evolve and become sentient or intelligent. And they would have, in fact, developed technologies for visiting other planets, such as Earth. And to close this out is you simply go back to the 1930s and go forward in time, you'll find thousands of citations on the internet finding spacecraft with apparently intelligent entities that are visiting Earth. This one guy, Stephen Greer, has a list of over 600 credible witnesses to these UFOs, unidentified flying objects. And if that's the case, then it's not out of the question that these other entities have been involved in influencing life on Earth over the millennia. So it goes. So these are the foundational questions. We're going to end it here. Bruce, any comments?
Wow.
No, it's Ron did a great job. It was just we ran out of time. There was just not enough time to explore everything, and we went after this and that and the other thing. But if we had more time, we probably would have done it differently. So, but
Yeah, if you had him for another 10 years, it would have been quite different.
Yeah. It was sad. He had a different. I forget what did him in.
It was cancer, wasn't it?
Alzheimer's.
No,
It was Alzheimer's? Wow.
Yeah, it was. What's surprising is there's a lot of evidence that, especially when people do these. Let me get rid of this. When people do these hypnotic regressions into past lives, they end up actually dealing with the soul, or with the soul is linked to some greater collective unconsciousness, is what they think is going on. And they ask the soul, well, one of the reasons why the person has come there for this hypnotic regression session is they have some illness, that, and they want to see, so maybe there's some past life where I did something terrible, and that is being reflected in this life. And so, like, for example, one person had incredible pain in their right eye, which was due to a buildup of fluid there. And so they regressed to this past life, and they went through this study. But then they asked the soul, well, are you aware of this physical problem? And it says, oh yeah, we've been waiting for you to ask about that. We're going to go fix it right now. And just while they're talking with them, all of a sudden the pain disappears in the person's eye, and the fluid gets all drained, and the person healed himself. Done. End of story. And it's funny that Ron didn't go in that direction and just try and think through how to. He was focused very much on his own observations, and I don't know that he ever thought about doing something like that, asking those sorts of questions. But once you ask them, then the body heals itself. You heal yourself anyway, because you cut yourself, you heal. You have thousands of cancer cells every day that get killed in your body, and so it goes. So it's just one of these things that we ran out of time. We never explored it in any detail. We did what we could. I've gone through kind of everything he gave me, and I keep visiting it to make sure I don't miss anything. And I think I'm pretty well at the end of what we did. You know, he had some other things. I think they would be you know, of limited interest. So, but I'll keep looking to make sure. How is his book sales going? You get any royalty checks ever?
Yeah, I do once in a while. Not very much though.
Yeah. No, I get royalty checks from Amazon, you know, every so often. So I co-authored a book a long time ago. So anyway,
Right.
so that's the foundations that we've got that we're going to deal with in this class this year, and we will start next week with a new go at it of new material. We keep revisiting it, but then it's incredible. There's so many things that are out there now that weren't there
Right.
5 years ago. It's not even close. So we're just trying to keep up.
We were in touch with some animation artists in Ukraine who are really wonderful. And we're thinking it might be interesting to have them look at bringing Ron's drawings to life as animations. What do you think about that?
Well,
Yeah, they're in Western Ukraine, in Lavina, I forget. There's a big town in Western Ukraine. So even though the Russians are trying to destroy everything, they're still safe.
They speak
right.
excellent English,
Yeah.
and they seem to be extremely capable and
Oh yeah, look at they're taking
Up to
apart the
date.
Russian army. They're capable.
Yeah.
So we'll see what happens. Anyway, have a good weekend. Next week,
Okay.
another week.
All righty.
Okay, go get them. Have a good.
stay warm.